Hi Chemistry, Unit 1, Revision PowerPoint, Chemical Changes and Structure. Over several years, various scientists tried to come up with how to put the elements that were known at the time together. Newlands were one, came with the law of octaves. But the major person involved with this was Mendeleev. And he played cards with them and put them in order of atomic mass, or atomic weight as it were known then. The good thing about his was that he left gaps, and into those gaps it was able to predict elements that hadn't been found yet. The elements these days are arranged in atomic number, which is the number of protons in the atom's nucleus. They are arranged in groups, group 1 to group 0, 1, 2, 3, 4, 5, 6, 7, 0, and that number indicates the number of electrons in their outer shell. There are some groups that you need to know, as you can see from the diagram. They're also arranged in periods, and the metallic properties of the element alter as you go along the period, from left to right. There are various types of bonding. First one to think about is metallic. In this you have a sea of delocalized electrons inside a positive metal ion nucleus. This is why metals have properties like shiny, being able to be bent and things like that. In non-metal you get covalent bonding. This is where the shared electrons are pulled on by positive nuclei. Covalent bonding comes in two flavours. Small molecule, called covalent molecular, where this is things like sulfur and phosphorus, which are solids, and gaseous molecules, as well as covalent network. These are things like carbon, silicon, and boron, which effectively are one giant molecule. Group 0 or 8, whichever you want to call it, are monatomic, meaning singular atoms. They don't react with anything. The previous bonding noted, metallic and covalent, and ionic when we get onto it, are all intramolecular. They're inside the molecules. But also present are intermolecular bonding. These being London dispersion forces, where for a minute second the electrons are all on one side of an atom, so therefore that side of the atom finishes up with a negative charge. This induces a negative charge and positive charge on the near atom, allowing intermolecular bonding between the molecules. The bonding structures of the first 20 elements is given in the table here. Metals to the left, boron, carbon, silicon, which are carbon networks in the centre. Nitrogen, oxygen, hydrogen, fluorine and chlorine are all gases and covalent molecular. Phosphorus and sulfur are solids, covalent molecular, and the noble gases are all monatomic. Melting points and boiling points of metals fall as you go down the group due to the atom getting bigger, so being less tightly held together, but rise as you go down the group in group 7s and group 8 due to the size of the molecule increasing, and so an increase in the LDF forces. Covalent networks have very high melting and boiling points due to the fact that you're not breaking intermolecular forces, you'd have to break intramolecular forces. So that would be breaking the actual covalent bonds. Trends in the periodic table. The atomic size decreases as you go along a period. This is due to the increase in the number of protons, so the nuclear charge gets bigger as you go along a period, which pulls the electrons closer to the actual nucleus. The covalent radius gets larger as you go down a group, just because you've got extra shells being added to the actual atom. Electronegativity and ionization energy share the same pattern. They increase as you go to the top left-hand corner along a period, and they decrease as you go down a group. This is due again to the increase in the nuclear charge, pulling electrons closer, holding them tighter, and as you go down the group, due to it gets less because of the increase in the atom size, the distance from the nucleus that the electrons are. Plus, you also have the shielding effect from the inner electrons, which use up some of the nuclear charge, meaning it pulls less. Bonding in compounds. Ionic bonding. generally between metals and non-metals, between atoms of different, largely different electronegativities. It's where the metal loses an electron, the non-metal gains an electron, and they're held together by electrostatic attraction. Think of magnets north and south. Covalent bonding, as mentioned earlier, electrons being shared and pulled on by positive nuclei. Covalent molecular bonding can also come in two types. There's non-polar covalent bonding, where the atoms have similar or the same electronegativity, and there's polar covalent bonding. In this, there is a large difference between the electronegativities of the atoms, but not enough to make it ionic. So one side of the atom finishes up with a slight negative charge, the other side of the atom finishes up with a slight positive charge. This will obviously give intermolecular bonding. The bonding continuum gives us an idea of how all these fit together. With ionic bonding, where you've got extreme variances in electronegativity, and non-polar covalent, where there's little. As mentioned earlier, there's intramolecular forces. These are inside the molecule, and intermolecular forces. These are the ones between the molecules. This is where the London dispersion forces comes into, where the polar covalent molecules come into it. Another name for intermolecular bonding are van der Waals forces. The weakest of the van der Waals forces is London dispersion forces. This is where the electrons, by random movement, finish up on one side of an atom, and that gives a slight negative side to one side and a slight positive to the other. The second side, the permanent dipoles. This is where the atoms making up the molecule have differences in electronegativity. These leads to permanent positives and negatives on each side of the molecule. The strongest of the van der Waals forces is hydrogen bonding. This is a special kind of permanent dipole whereby the hydrogen is bonded to oxygen, nitrogen, or fluorine. This is what gives rise to the high temperature that water boils and freezes at. And you get the same properties with hydrogen nitrogen compounds and hydrogen fluorine compounds. It's intermolecular bonding that gives rise to properties like solubility. A polar solvent will dissolve polar substances or ionic substances. Water will dissolve salt. A non-polar solvent will dissolve non-polar substances. So wax will dissolve in petrol. Also, properties like viscosity and miscibility are down to intermolecular bonding. OH groups, especially on alcohols, will allow them to dissolve into water and will allow hydrogen bonding between compounds, organic compounds. Hydrogen bonding is also the reason why ice floats in water, as it doesn't allow the ice crystals to get close enough together, so it means the ice is actually less dense than the water. As mentioned earlier, covalent network material have high melting and boiling points because it's the actual bonding internally, it's the intramolecular bonds that you're breaking to melt them. Redox reactions. This is short for reduction oxidation reactions. This is where atoms within a reaction will exchange electrons. Metals generally lose electrons, and so they are oxidized. Non-metals generally gain electrons, so they are reduced. It is possible in displacement reactions for both things to be metals or for both things to be non-metals. The idea is that if it loses an electron, it is oxidized, so it's a reducing agent. It's making something else reduce. Good oxidizing agents are things that make something else reduce. So they will be the metals at the top of the electrochemical series. Good reducing agents are things that make something else oxidize. So they would be the non-metals at the bottom of the electrochemical series. When looking to add redox reactions together or balance redox reactions, one of the first things you must do is ensure that all major elements are balanced first. Then you look to balance the number of electrons as you're going through it. After you've balanced the main elements, then you balance up any oxygen by adding water to the side without the oxygen on. Once this is done, you add hydrogen ions, positive ions, to the side. Once the hydrogen ions have been added, then you add electrons to the side that's got the most positive to balance up the charges. It should be negative, what should equal each other overall.